So before the break, I asked you this question. So we define security with you cannot win, the adversary cannot win with probability half, versus the absolute difference from a half is negligible. So is this the same? I get a yes. It depends is actually the right answer Yehuda just gave. In general, no. So the problem lies in this thing, right? The adversary could deliberately choose to lose. Let's say with probability 3/4, it just makes a reveal for some identity, and then it immediately makes a test on the same identity. And that will give a probability of winning of, let's say, less than a quarter. And then, of course, in terms of absolute values, a quarter minus a half is still a quarter, right? So it wouldn't be negligible. Now, still, in the literature, you sometimes find this definition. And this is why Yehuda's answer, it depends, is correct. Let's say the adversary decides, I'm going to break freshness by testing and revealing the same identity with probability 3/4. Well, you're the adversary, you're allowed to do whatever you like. But our idea was to punish you if you misbehave in a trivial kind of way. And you're going to misbehave badly, and then you get a probability of winning which is less than a quarter. 2 questions. Say it again? Exactly, but this adversary which decides to lose, so the question was, aren't we quantifying over any adversary? But this specific adversary which decides to break freshness with high probability has a probability of a quarter here, minus a half. In terms of absolute value, this is a quarter, not negligible. Right. Right. The counter argument is that I can build an adversary just doing the opposite. The thing is, you can do this with encryption, where you just output a bit. Right? If the bit is deliberately wrong, I'm just going to flip the bit. But here it's not only a bit which you output. Here you have some additional condition. It's that one. And that I cannot flip easily. Okay.
What are the rules? If you violate this rule, then you lose the game?
Yes. We punish the adversary for misbehaving. Now still, in the literature, you often find this definition here as well. And what the people do is they don't punish the adversary in saying you lose, but they disallow the adversary to make such queries. They say you cannot, as an adversary, you cannot make a test query on a session which is revealed, or vice versa. Okay? So they put the burden on the adversary and they restrict the adversary. I haven't restricted the adversary, I punish the adversary afterwards. Interesting question, are they equivalent? I don't know. Okay, so let's get back to active adversaries. Okay, so we think of in terms of identities as public keys or certificates. This may be the common domain in the certificate, whatever. Just think of there's a unique or the serial number of the certificate. Just think of these identities are unique and somehow they are in the certificate. Okay, this has some implications if we talk about security models. First, now every entity has an identity, right? So we're going to assign user identities to each party. Then each user under some identity also needs to have the public key, secret key, and the certificate. So this is given to all users at the outset. And now that you have a long-term key, like an encryption key or a signature key, you may want to consider the possibility that the adversary suddenly has quantum power and breaks the RSA key, right? So we may consider the possibility that the adversary gets the public key and is somewhat able to compute the secret key. Okay, so this is how it affects the model. So we're going to add a corruption query for the latter. So first we now have the set of all public keys of all the users in the universe, and this is generated at the outset. We don't have revocation and so on, and then it's given to the adversary. Right? Public keys are public. They're on some server available, and you can just download them. Now, before we had that, you can just press a button and then you get the transcript of the execution. Now we have identities. They have different public keys. They may use the public keys in the executions. So this means that the executions are not equivalent anymore. It's not like pressing a button and I run the anonymous protocol between two parties. Now they may use the public key. So this means the adversary now specifies, I want to see a session between this client and this server. And then you run the transcript, of course, for these two parties, involving their public keys. And now we add the corruption. It takes into account the possibility that the adversary recovers the secret key. So what the adversary can do, it can just specify a user identity, and in return it gets the long-term secret key of the user. And it can do that multiple times, of course. Okay. So now that we have augmented our model, or the capabilities of the adversary, it also means the adversary has more possibilities to attack protocols. So here's an attack which hasn't been available before. So let's say the adversary tries to impersonate this client. So it can corrupt the client with this new corrupt box. It gets the secret key. And then it just impersonates the client towards the server. The server says, okay, I've seen maybe there's some message saying here's my public key, here's a certificate, and maybe the public key is later, the secret key is later used as a signature.
You said there's the public key, the secret key, and the certificate.
Yeah.
What's the certificate in relation to the public key?
The question is, what is the certificate in relation to public key? Typically, you can think of the public keys embedded in the certificate, right? This is what you would do in practice. Sometimes it's in crypto, it's more convenient to keep the two separate and maybe only talk about public keys, and then it's understood that the public key comes with the certificate. Essentially, you can think of this as one entity. Yes, certificate carries the signature of some authority, exactly. But for now, we can just think of this is your public key and it's certified somehow. Okay, so what I can do here as an adversary is, now that I have the secret key, I can just pretend to be the client, right? I can, for example, sign now on behalf of the client. And then I can just test this server here. And of course, the adversary, since it has full control over the client here, also holds the key. And if it holds the key, it can easily distinguish this key from random. So this is one possibility to break protocols now. And this happens, I mean, typically people don't, or it's much more convenient to force parties to use given keys than breaking public keys or revealing secret keys from public keys. But this happens in practice, right? That, for example, agencies go and just pretend to be Google, and then users connect and reveal their passwords and so on. But again, it's typically not through corruption, but through rogue certificates. But in our model, you can think of this as a corruption, right? I corrupt, I have the secret key, and so on. So corruption is not, there's different ways also in the literature how you can define things there. One of the questions is, if I corrupt you, does it mean I break into your computer and I read the secret key from your computer? But then I can also potentially read more, right? Maybe some randomness, some g to the x, and I can find the x value in the memory. Maybe I can't, maybe it's hard. If you think in terms of the quantum attack, right? I'm breaking RSA, your RSA key, because I have quantum power. then I don't recover your state, your inner workings of your computer. I just recover the secret key. Both have their meaning. Both can be used and defined. Sometimes you find in the literature the distinction, this is called a weak versus a strong corruption, where weak means you just get the secret key, and strong means you get the entire state of the computer. Now, for some reason, typically nowadays, people think if they just write corruption, they usually think of weak. Now, another question is, once I corrupt the party, does it mean I completely take over? So does it mean I break into your computer and I disconnect everything, right? I have full control. I can decide if it sends messages, and I can block messages or not. Or does it mean that I just get your secret key, but you're still active? And what we do here in this talk is we focus on the case of so-called weak corruption. So we only get the secret key, and we also allow the party which is corrupted to still be active and still run executions. Okay, so now that we have identities, the question is,
What about getting the randomness of the party in a session, but not their long-term secret key? Something that we were mentioned yesterday.
what about attacks where you get the randomness but not the long-term secret key? I'll come to that. This is like in this direction of ECK model and so on. I'll get to that later. Yes, the question was if I get the secret key and then I disconnect the computer of the client, basically, right? Yes, you can do that because you have full control over the network. The question is, can I still say to me, the adversary having full control, can I still say to the client, please talk to that server, right, again, and just run the execution with some fresh randomness or whatever. And that's the distinction here in the second case. Okay, so now that we have identities, we can talk about different forms of authentication. One is anonymous. Basically, you have no idea whom you're talking to. And this was the case of G, if I send G to the X and G to the Y, some ephemeral secrets, no long-term secrets involved, and so on. Then you have the unilateral case. This is where just one party authenticates. So in particular, one party has a long-term key and a certificate. And then at the end of the execution, not only do they get the key, but the client also is somehow assured that the intended partner is the server. Or actually, maybe if you like, it should be, it is the party behind this public key, to be precise, right? And you have mutual authentication where both parties authenticate. Now, the typical case in TLS is unilateral authentication. You connect to Amazon, you get a certificate of Amazon, and Amazon somehow proves that it is Amazon you're talking to, but you don't authenticate. You know why? What was that? Maybe you cannot. Exactly. That's one part of the answer. Maybe you cannot. If you want to have a certificate and it's valid, it's recognized by your browser or by Amazon and so on, you have to pay for this. A couple of $100 maybe $100. There are self-signed certificates and so on, but if you want to do it properly, like the way Amazon does it, you have to pay for it. And this would be too much burden for customers. If they want to connect to Amazon, first they have to invest $100. So what do you do instead? That was the password, exactly. You first run the key exchange protocol, and then afterwards use the channel you send your password. Maybe hashed, maybe in a more complicated way, but this is how you do it, right? You authenticate then on the application layer, not on the key exchange layer. But then this is, by the way, this is out of question for security of key exchange, right? We talk about key exchange, not what's happening on the application layer. So from our perspective, this is a unilateral authenticated key exchange. Okay, so another change besides the identities that we need to talk about sessions. I used the term session keys a couple of whiles, but so far I tried to avoid the term sessions. And the conceptual change is due to the fact that now the adversary is active. So before we had, you can push a button, the adversary can push a button and then gets the transcript of an execution between two honest parties. And it was clear who was talking to whom. So now we have an active adversary, right? And now we have a server talking to someone, and it's unclear to whom it is talking to. It may be the adversary, it may be a client, it may be first a client, then an adversary, and so on. So this is why you now have to think mentally of sessions. And a session is just one side of the execution, right? Forget about this. Not valid anymore in the active model. Think about incoming and outgoing messages. This is what you have to think about now. These are sessions. There may be a partner, there may not be a partner. Okay, and how does this affect our security model? Active adversaries can intervene, they can send messages and so on. We're going to add this. You see in a second, I removed the exec oracle. Okay, so we're going to add the possibility. So now we tell the adversary, it can just tell some identity, some session, here's the next protocol message, right? So this would be the incoming message, and then the protocol or the session would answer with, this is next message, right? Immediately give you the protocol answer. And then the sandbox would just return exactly this answer from the session to the adversary. So now the adversary communicates step by step with that server. And of course, you also technically need to have some possibility to start a new session. Yes, there's an init, special init command and so on, but we can neglect that for the moment. Okay, so exec disappeared and was replaced by send. Question is why? Why can I do this? You can stop execution?
I don't mind what goes on after some point.
Okay. But what if my attack relies on, okay, I run an honest protocol execution 3 times, like between client and server, and then suddenly I can break it. You don't have any exec oracle here anymore, right?
Just send the same message as the real person and get the next message.
Exactly. You can simulate, that was the answer, you can simulate the exec oracle through the send oracle. So this is what you had before, right? You can run an exec, you push the button and you get the transcript. So now we can simulate this by just send queries. So again, there needs to be a special init message. So you just start the execution saying, okay, please client start a session. The client will send you the first message, and then you can just send it to, well, you probably need some init here as well. You can send it to the server. The server would respond, and then you can just send it to the client session, getting the response, sending it here, and so on. So you can just relay the communication. So there's essentially no need to have exec anymore. There's a small footnote here. Sometimes you may want to still have the exec when you talk about forward secrecy, but I'm going to remove it for now. Okay, no exec anymore, just sending. So the question is, what happens now to the freshness condition that we have an active adversary, right? Okay, so this is the example. Now, instead of running this exec, I'm going to exactly this. I'm the adversary. I'm going to exactly forward the messages with send queries. This is as good as running an exec between 2 messages. Now, what's happening is, of course, since this is like an honest execution, they're going to derive the same key here. And now I need to make sure that I cannot ask to test this session and reveal this session. So before it was very easy to capture this, just saying the key is attached to some identifier, some ID value, and I cannot test and reveal the same ID. But now what we have is this notion of sessions, right? We think of this as separate executions, outgoing and incoming messages. So we need to make sure that there's no trivial attack, right? The adversary mounting this attack, relaying the messages, and then testing, revealing on one and the other side. However, in general, we don't know if these two messages are, if they belong together. Okay, so now what we need is a notion saying, basically, this is like an honest execution of these two sessions. They are linked. And this is called session matching or session partnering. And as I've said, we have many security models. There are different ways you can do this. So in the original Bellare-Rogaway paper, we had a notion called matching conversations, and I'm going into that in a second. Then in the stock paper, they changed it to something which is called the partnering function. And then in the BPR paper, they used so-called session identifiers. Again, they all have the common understanding that you want to be able to recognize which session belongs to which session. They just implement it differently. Okay, so here's matching conversations. In the original definition, matching conversation said the two sessions are partnered if they have identical transcripts, so incoming, outcoming messages correspond to each other, and they're in the right chronological order, saying that in the protocol execution, this message was really sent before this message. The content is the same, but timely, this was sent first. Then the answer came before the answer was forwarded to the other session. So it's really also about the chronological order. So sometimes what you find in the literature is that people drop the second part and just say the transcripts have to be identical. Which one do you prefer?
So we're in a model where there's no information from where the message came from.
Yep.
Just the message itself.
Yeah. You have just incoming, outcoming messages at one point. You can do it by majority. Who wants to have the one with chronological order? Raise your hand. Oh, a few. Who wants to have the other one? And the rest is undecided. So what is the advantage of the first one? It's closer to a correct. Yes, this kind of gives you a stronger notion of things are tied together, right? Because they need to happen in the right order. Replay attacks? Sorry, what was that? Yeah, at this point we're not really talking about replay attacks. Now, if you can detect them, it's just about saying, oh, this endpoint and this endpoint, they belong together. Right? Okay, question.
Accounting for adversaries reordering messages?
This one does.
The chronological order one?
Yes. So it seems to be the better choice, right? Stronger security. Here's an example of a protocol, right? Let's say you have a protocol which is secure according this chronologically ordered message flow. Okay? And now I'm going to add two messages to this protocol. And the messages are, I sent a 0, and the other one responds with a 0. Intuitively, it shouldn't do harm to the security of the key exchange, right? But now, as an adversary, I can make these two sessions not be matching according to chronological order. Why is that? Because I can predict messages, right? So I'm going to run this. This goes here. This is the first message, as before. These are these two. Fine. Now I get the 0 here, and I'm going to answer 0 immediately, because I can predict that the other guy will send a 0. So I get this message here. I'm going to now forward 0 here, get the 0, and I'm going to finish the protocol. And now you see they're not chronologically ordered anymore. This means, if I have this idea that then they don't belong to each other, I can test and reveal each side. And since they don't belong to each other, that's fine, that's admissible. Of course they derive the same key here, right? Because the zero message don't do any harm. Again, is this a fault of the model? Is this a fault of the protocol? Who knows? Okay, so I said there are three possibilities to define partnering: matching conversations with the two subcases. Partnering function. Partnering function was introduced in the BR95 paper, and they had something they said, let's be very general. Let's say you have a so-called partnering function, and this partnering function may not be even efficiently computable. Maybe an arbitrary mathematical function. And then we say two sessions are partners if I apply the function to the transcript, they end up in the same value. I think this notion of partnering is only used in the BR95 paper. For the fact that it's simply too strong, right? Now you have an unbounded function. You have no idea how to simulate this, maybe. You have no idea what kind of additional information this may give you, and so on. And it was essentially dropped in the 95 paper, after the 95 papers. Okay, so you can more or less ignore this. Last one is session identifiers. Session identifiers now says, you as the analyst or the protocol designer, you have full power of how you want to define partnered sessions. So what you do is you define so-called session identifiers. And you see we keep on adding more identifiers. Partner identifiers, user identifiers, identifiers for the executions, session identifiers. Okay? And there's no restriction on how you define this. Now, to give you a hint, typically what you do is you can define the SID to be the transcript. Sometimes it's not the entire transcript, but only parts of it. Gives you a different kind of binding of sessions together, but that's up to your choice. Now, if you define it over the entire transcript, for example, we are back to this case here, right? We don't care about, in the session identifiers, we don't care about chronological order, but we want to make sure that incoming, outgoing messages match. So they are then equivalent. Okay, and if people now, the literature, I don't know, maybe it's 50-50, maybe 60-40 for session identifiers and matching conversations. Both are doable. And it's a matter of choice what you prefer. Okay, so if you use session identifiers, and I'm going to use them because I prefer them, I like the flexibility of being able to specify how I see partnered sessions and so on, with the risk that I'm too loose on connecting things. Then there are some restrictions. There's some trivial cases. Okay, here's an easy example. Let's say I have a protocol. Okay, running here. And I'm going to say the session identifier in every session is empty. Right? Even in sessions which are run by other parties. Session identifier is empty, the empty string. Fine. Now, everyone is partnered with everyone. That's the meaning, right? They all have the same session identifiers. But this is not good from a security perspective, of course. Because it means that I can add, for example, test this session and reveal this session. Although they are completely independent, right, the executions here. But they're partnered according to my definition. I cannot do that. So this is too liberal. So I don't want to have that. So this is managed by saying that within within the entire attack or environment or execution, there are no three honest parties which end up with the same session identifiers. Yes, yeah, two-party sessions, client server, no three-party scenario here. Okay? Then the empty session and the identifier doesn't work anymore, right? Because it's easy that 3 parties have the same session identifiers, which is empty. Okay, here's how you could do this. Okay, you want to satisfy this condition. What I'm going to do is, running the protocol, I'm just going to output a local random string. And this guy is also outputting a local random string, completely independent of each other. Fine, now random strings, they're sufficiently long, no 3 parties will have the same session identifiers. But now you can, exactly, now the problem comes that if they're not partnered, I can again test and reveal. Okay, so I can't really do this. And typically, so the 2 conditions are, the following are more or less functional. The first one says, if you have an honest execution, you also want to have that the session identifiers really coincide. Right? This local randomness, not a valid solution. If you define it over the transcript, for example, done, right? Because then both parties have the same session identifier as well. And the third one is saying, if they are partnered, if they have the same session identifiers, then I also expect them to hold the same key. Right? This is just saying, if you say these 2 sessions belong together, then they should really belong together and they should have the same key. Okay, so how do you define uniqueness for session identifiers? And it's not too hard. Here's what you do. You just have the parties, each party send a nonce, a random number, or a counter, or whatever. It's something which doesn't appear twice. And now if you define the session identifier over the transcript or parts of the transcript, they appear here in the nonces. And now it's clear, if one of the parties is honest, it will choose a fresh random value for the nonce, and then you don't have any matching session identifiers across 3 executions or so on. So it's very easy to implement this. And in fact, you see this quite often in practice that, you know, client and server exchange nonces. I think this is less to satisfy the theoreticians, and practitioners don't care too much about session identifiers, I would say. But this is the kind of understanding that you exchange nonces to make this execution somehow distinct from the other executions, right? And in the security model, it's reflected that now you can talk about session identifiers. And TLS in both versions, 1.2 and 1.3, they do this. Question? What happens if an entity repeats a nonce? This is why you have both sides contribute, right? They both pick a random nonce, and you basically concatenate it in the session identifiers. So let's say in the second execution, the client sends again the same nonce. Then the server, at least if one of the guys is good, will pick a fresh nonce, right? And it's yeah. Yeah, absolutely. This could be the client, maybe some misconfiguration or whatever, but it can also be an attacker. And the attacker can do this over and over again, right? Just keep on sending the same nonce. But every time the server will pick a fresh nonce. Birthday bound, yes, of course. Nonce should be large enough. TLS 1.3 now has 256 bits of nonce. So repetitions shouldn't appear. Yeah, yeah. If you use a bad random number generator, things are different. Yeah, but this is also something we assume, right? We assume that signature schemes which are used, MAC schemes which are used, are good. Pseudo-random number generators are good. Does the derived key depend on the session identifier? Usually it does.
Because without it, you can think about an adversary in the middle, making them share the same key, but have different session IDs because it changes the
Yeah. Yeah, this is one of the problems, right? I told you that now you have the freedom to choose your session identifiers the way you want it to be, but you need to be careful that you don't risk or harm security by having wrong choices. So the common choice is the session identifier is about at least most of the parts of the transcript. And if you think the transcript determines the key, then things should be okay. But again, this is very specific to how you pick, how the protocol looks like and how you pick the session identifiers. Okay, so this means we can now rework our definition of freshness. Okay, whatever kind of partnering you choose, right? If you choose matching conversations or session identifiers, fine, but you get to pick, right? You say now these two sessions are partnered if session identifiers are identical, if they have matching conversations and so on. And now we're going to say the freshness condition is that neither the test session nor the partner session of the test session is revealed, right? So you have this. Let's say you test this one, and you say that these are partnered. They have the same session identifier. Then I cannot make a reveal on this one. Right? Because if they're partnered, according to session identifiers, they also hold the same key, and this would be a trivial attack. Okay? And secondly, we added the corrupt queries. And now we say that, of course, if I test a party, this party cannot be corrupt. The party is corrupt, I'm not going to protect it against anything, okay? Not really be sure that I can protect it against anything. Nor is the intended partner if it's mutually authenticated, right? Then I have a feeling I'm talking to this client. And of course, then this client cannot be corrupt, because if it's corrupt, right? So the adversary can just take over, make a corrupt on this guy having the secret key, and just execute the protocol itself, keeping the client out of the loop. And then, of course, it can compute the key. Right? This is what we're going to exclude in the second case. Now, if we talk about unilateral authentication, and this should be if authenticated partner in the test session. If you talk about unauthenticated, so you don't expect to be talking to someone specific, then it must be that there's an honest session. And what this prevents is the following. So let's say you have unilateral authentication, classical TLS setting, right? So they talk, and now this guy thinks, hey, I'm talking to the server S, and this guy has no clue whom he's talking to. If this guy doesn't know whom he's talking to, and you want to test that session here, it could also be that you talk to the adversary. And then again, you can win trivially. So if you don't have an authenticated partner in the test session, then there must be an honest partner session. So there must have been really another party which contributed to this, right? So there must be some party which has actually sent these messages. Question?
What's the point in revealing the key or getting the key when the other party doesn't even know what the key is? How, you cannot convince the client that this should be the key.
I'm not sure if I got the question.
He has a key that he created together with the server, so what?
Yeah. Yeah. So you're talking about the previous case, right? So this guy, so it's unauthenticated. Yeah, but you still want to, that this key here is, for example, secure against outsiders. Outsiders, passive adversaries, just observing the traffic. Maybe, because you have no idea, right? It's unauthenticated. Maybe it was created with an honest party. Then, of course, you want the adversary not to know this key, right? In terms of model, it means you can test it. That's the thing. If you can test and you can distinguish it, then it's still good. But since it's unauthenticated, you have no idea if you talk about this case or this case.
No, I'm talking about the previous case.
Yeah, but yeah.
So, in that case, you have that the adversary talk to the server, exchange the key, and that's it. The client doesn't even know what this key is, so he cannot use it.
Exactly, but the thing is, if you think in terms of, okay, the adversary talks to server, so it's unauthenticated, what security guarantees can you give about this key on the server side? Exactly.
But I don't care.
Yes, but this means I don't want to have it in the test session, because the test session is about this key is still good. You can't distinguish it from random. You can just interpret it as, oh, the key is still good. Now, in this case, this key is not good, right? Because the adversary may just hold it as well. But then I don't want to have it in the test session. I cannot allow the adversary to test it because that's easy for the adversary to win. But I'm not claiming any security about this key. This is why I exclude this. It's already corrupt, exactly. There's nothing to, I don't want to protect this key. Okay, in the anonymous case, it says there must be some honest party which is connected to that party, right? To the test session party. Meaning again, I'm excluding the case that the adversary talked to the test session. Must be some honest party, but then I still want to have security of the key, secrecy. Okay. Now this is the security model of authenticated key exchange now. We filled in some parts, we removed some parts like the exec and so on, but this is it. Right? You're saying we have the public keys, you can run executions, initiate sessions of course, you can test, you can reveal, you can corrupt. And the adversary wins if it is able to predict the bit B, hidden here in the test oracle, and if it satisfies the freshness condition. And freshness condition is just, a template for, if you talk about mutual authenticated, then it means, then it means not revealing the partner or the session itself and not talking to a corrupt party. And if you talk about unilateral authentication, you have the same plus this condition. Doesn't matter, just plug in your freshness condition and you get security. And then you say the key exchange is BR secure against active adversaries if for any efficient adversary this is at most a half. Plus, I mentioned this, if you use session identifiers, you have this condition on the SIDs as well. Right? For example, no three parties derive the same session identifiers. Questions?
Just to clarify, if the session ID is done only by sending nonsense and buying to nonsense, and if it is a unilateral authentication, then in that case you can make an attack by simply dropping the.
Yeah, so your question was, if I understood correctly, was, okay, let's say you have nonces and then you do the actual key exchange. And now the session identifier is just the nonces. Yes, then as an adversary I can step in from here on, right? For example. This is why typically the session identifier includes much, much more from the transcript. It somehow needs to be bound to the key, right? So you want to have more than just nonces, random numbers exchange, and this is your session identifiers.
Do you take it for granted for your analysis that you have this session ID assigned according to your assumptions or requirements?
Do we take it for the analysis?
On your own, are you going to tell us how to make session IDs that follow these three requests? I think like three.
The question is,
Or do you leave it like a problem for engineers?
no. So the question is session identifiers, how to pick them.
Yes.
Very roughly, this was the short version of the question. This is up for the crypto people, right, who design or analyze protocols. They need to specify session identifiers. Session identifiers may be only a virtual thing, so they're only used in the analysis. You may want to use session identifiers in real life as well. If you say, I identify sessioners according to session identifiers, you may pick so. But we have to, as cryptographers, we have to specify these are my session identifiers, and then we have to check that no three honest parties have the same, or with small probability only, and so on.
So you actually give sort of recipes for specifying.
The recipe is very easy. Session identifiers should include the entire transcript, or almost.
But what is means that an adversary in the middle could change transcripts to do various things?
Yeah, fine. And for example, if you, we'll get to this later, if you include all the information which is in the session identifier also into the key derivation, then it means if you change something in the session identifiers, you also change the keys. But again, parties do not need to know session identifiers in the protocol. They may, again, if it's just a transcript, they may as well compute them themselves, but typically it's not a part of the protocol specification. It's part of the analysis.
In the anonymous case, if the protocol is just simple experiment, does the man-in-the-middle attack count as a successful attack?
So the question is, oops, if it's just Diffie-Hellman. So this is anonymous, right? Plain Diffie-Hellman, and then you can only test, you're only interested in protecting the keys which have been derived with another honest party, right? The adversary does not interfere, it's G to the X, G to the Y, the adversary shouldn't know that key. And this is still okay. If you have such a session, you can test it, right? Because it's still fresh. If you have an honest partner, then it's fresh, you can test it, this means the key is still good. Now if you, there's no such thing, the adversary has sent G to the Y, for example, then there's no honest partner, you cannot test it. I'm not going to protect against keys which the adversary may know anyway.
So you're not protecting yet against man-in-the-middle.
You're protecting against man-in-the-middle attack the best way you can. Right? If you think about, we don't exclude man-in-the-middle, right? I mean, it's depends on if man-in-the-middle just forwards, relays, or if it does some changes. Right? If it just relays, we're protecting against that. Right? Because it's G to the X, you forward G to the X, G to the Y, G to the Y. You have an honest partner, and the adversary, of course, doesn't know. But it hasn't touched the execution, right? This is just saying it's like exec. What's that?
So it's not really in the middle.
Yeah, it depends on what you mean by man in the middle. Does it interfere with the protocol execution or and so on?
Otherwise, it's just equivalent logic.
Yeah, exactly. But in the anonymous case, we cannot protect against more than eavesdropping, right? Because if the adversary sits on one of the sides, of course he may know the key. Okay, so this is the formal definition. Here's what you intuitively get from an authenticated key exchange and what authentication here actually means. So I like to think of this as if I complete a session as an honest party, then I know there's at most one other party holding the key. So this is the less or equal to 1. And if it's some authentication mechanism there, then of course I cannot protect against dishonest partners, right? If I'm talking to the adversary and I know that I'm talking to the adversary, then the adversary may know the key. But if it's, and the adversary may not compute the key eventually, but if it's an honest partner, then I know it's that party. That's intuitively what you get. Okay, question? There's at most one other party holding the session key. Why can't it be 3? Okay, there's one case. One case, it's two honest parties plus adversary, right? So they hold the session key and then the adversary. Now that's a bad thing, right? If the adversary knows the key of these two guys, it's broken, essentially, right? I mean, unless they are badly, no, it's definitely broken, right? You can test these and just compare it to the key which you as the adversary has in mind. Okay, that's the easy case. What if it's 3 honest parties? Whoops, too many? Exactly, right? So let's say you have 2, and let's make it life a little bit simpler. Maybe they are connected, they have the same key, and suddenly there's a third party which surprisingly also holds the same key. Okay, so the thing is, you said, okay, I can reveal that, and for example, test that one here. and then I just compare. Am I allowed to do that? Wait, sorry, what was that?
Well, yes, unless they share the same SID.
Okay,
Then you have everything which has like a partnership with underneath.
exactly. That's exactly the point. So there may be the thing that this guy, and this guy, they share the same session identifier. If you remember, 3 honest parties having the same session identifier, not allowed. Okay, so this cannot happen. So this guy, or one of the other guys, must have a different session identifier. But then they're not partnered, right? Then I can exactly mount this. I can do a reveal here and a test here. They're not partnered. I can do that. It does not violate freshness. And I can break security.
In this model, you can have a situation where you have 3 honest parties with the same key if the attacker first queried the key
Yeah.
from the first 2 and then he shared that same key with the third honest party.
If the adversary reveals the key and then... Oh, yeah. You can just mount... Maybe it's just I send you an encrypted key and then as a bad guy I reveal from one session, I send it to another honest guy. Yeah, but that's... exactly, that's about testing. Let's say 3 parties in a tested session cannot... Okay, true.
The session ID as you define it is mutable. It changes throughout the execution.
Ah.
Right? So the conditions you impose on the session IDs, are they applied to the final session IDs at the end of the entire execution at the time of the test?
Okay. Question was, session IDs are immutable, do they change over time? The way I look at it here, no, they don't change. They are basically, think of them, they are output at the very end. When you output the key, you also output, this is just a virtual thing. You specify this is now the session identifier. So it doesn't change over time. It is set to some false value during the execution and only at the very end.
If you choose the session ID to be the transcript evolves over time until it terminates.
Exactly, but you at this point you have the transcript. It changes. Then you end, and then you say this is my session identifier at the very end. So you don't change it, as the flow continues. There are cases where you want to do that, especially for TLS 1.3 because it derives a lot of keys, but that's a different story. Yeah, in principle, partner functions, matching conversations are alternatives to session identifiers. Yeah, again, partnering functions are not used. I don't know. Maybe it's a good strategy to revive them if there's a good reason. But I would expect that people are suspicious if you've started partnering functions. If you do matching conversations, then basically it's clear, right? Your session identifiers are specified through the matching conversations. I am, later. We're still in the plain BR.
No, because then the issue of sub...
Yeah.
You don't have the session ID only at the end.
Yeah. Not at this point. No state reveals at that point. Okay. As I mentioned, I like to think of this authenticated key exchange as at most one other party holds the key. There's also a notion called key confirmation, which says at least one other party holds the key. Key confirmation for me is a strange property. I should warn you, we had a paper about this recently where we tried to specify it. It's still key confirmation. It can also be that. So key confirmation tells you that at least one other party holds the key. Now, if you combine the two, then it's exactly one party holding the key. But key confirmation is per se not a requirement in the Bellare-Rogaway thing. So maybe that that there's no other party holding the key and you're just the only one. Yeah.
Can you maybe show the case where I do main the middle for regular big Kalman with, for example, no certificate to explain why it is not secure in the case of mutual authentication?
Diffie-Hellman in what? Which protocol? What Diffie-Hellman?
Regular Diffie-Hellman.
Okay, just G to the X and G to the Y? Okay.
And I assume that I send just the names of the party, not even the certificate.
Yeah.
So I want to prove that it's not a mutual identification protocol.
Yeah.
How do I prove such thing?
Or typically, for example, what you'd say, the SID is the transcript, right? Okay. And the key is G to the XY. So now here's my attack. I'm going to have G to the X. Client sends me something. I'm going to send G to the X, and I'm Eve. I get G to the Y under the server key. I'm going to forward this. Okay. So this guy derives G to the XY. This guy derives G to the XY. But these sessions are not partnered, right? Because the transcript includes E here and the client here. If they're not partnered, I can make a reveal here and a test here. Easily break it. Okay?
The attack where you start a new session in the other end, and you can reveal the messages yourself. It does not work in this case, right?
Say it again. If?
You can also make an attack where you choose your own the X as Eve.
Yeah.
So you can.
Oh yeah, you could even write compute G to the X here yourself, but then it would derive a different key here and there. Plus this partner would be corrupted.
So this is
No.
also like an attack in this model. Which is what,
Wait, you're saying this is an attack according to the model here?
yeah.
Something interesting to think about during the break. Let me just before I leave you into the break. Here's the question we had before. So far we said you have a single test query. Now let's say we want to extend the model. We're saying you can ask multiple test queries. Is this the same or not? Does it mean that I have a protocol which may be secure here, but not here? And if you think about this, think about what it means if you do multiple test queries, what it means for the test oracle, because you have to change the test oracle.